Very good morning, friends, and I warm welcome to all of you in the series of Mechanics of Solids. We are discussing right now the topic of bending stress in beams, and we are solving the numericals based on the bending stress, strength of material, unsymmetrical sections, and today is the last lecture about the bending stress in beams. So today let us be studied what we have studied up till now, and let us be solve some of the numericals related to the strength of section. So now that we learned in the previous session about the types of supports and beams, types of loads acting on the beam, determination of support reactions, plotting of SF and BM diagrams of a statically determinate beam, concept of bending stress and section modulus, concept of bending equations and moment of resistance. The objective of this session is draw the bending stress distribution diagram and calculate the maximum bending stresses in a given beam. Calculate the bending stress with symmetrical and unsymmetrical section. Let us revise what is bending stress. If we take any section of a beam and consider the free body diagram of the either side, we find that there must be the three internal resistance component which will be generated because of the application of the external forces. So these three internal resisting components are bending moment, shear force and the axial force. So the chapter here, the topic, we are discussing the effect of bending effect. So if we refer particular beam, we subject it to external load. If we take a section XX over here, then this section divides the beam into the two parts, the left part and the right part. At the section, at one of the part, the subjected to the bending moment, axial force and the shear force. The bending moment affected creates the compressive force on the top region of a section, and the bottom region is subjected to the tensile forces. This creates the bending stress in a beam. So here under the effect of the lateral loads, the beam bands and the longitudinal axis takes a curved shape. The beam produces an internal resisting couple to balance the bending moment due to the applied loads. This couple is generated by the normal compressive and tensile forces in the section. Refer over here. What will create the bending moment? It causes the compression on the one of the face and tension on the other. If we consider a simply supported beam, then top portion is subjected to the compressive force and the bottom parts or bottom fibers are subjected to the tensile forces. It also causes the beam to deflect. We have also derived an equation of bending equation. M over I is equal to F over Y is equal to E over R, and I wish you know all the nomenclature. What is the meaning of M, F, I, E, R and Y? And we also studied about the section modulus, that is Z is equal to I by Y max. It is the ratio of the moment of inertia of a section about the axis to the outermost layer from the neutral axis. Also we have studied the strength of section. M, that is nothing but the moment of resistance offered by the section. Also the moment of resistance is offered by the section is maximum when the section modulus is maximum, hence the section modulus represents the strength of section. We have also derived the equation of the section modulus for the known section, specifically the rectangular section, that is equal to BD square by 6. For hollow rectangular section, that Z is equal to 1 by 60 bracket capital BD cube minus small bd cube, where capital B and capital D are the outer dimensions of the hollow rectangular section, while small b and the small d are the inner dimensions of the sections. For circular section, Z is equal to pi by 32 d raised to cube, d cube. D is the diameter of section, and for the hollow circular section, the Z is equal to pi by 32 d bracket d raised to 4 minus d raised to 4, where capital D is the outer dia of the hollow circular section, while small d is the inner diameter of the circular section. Now, the bending stress in unsymmetrical sections that we have referred, let us be discussed in very brief. In case of the symmetrical section means the symmetry about x-axis and y-axis both. The neutral axis passing through the geometrical center of the section. But in the case of the unsymmetrical sections such as the L, T and unsymmetrical I sections etc., the neutral axis doesn't pass to the geometrical center of the section. Hence our intention, the first step is to find out the distance y from the topmost layer or the bottommost layer of the section from neutral axis, and that distance are also not the same. Hence, for finding out the maximum bending stress in the beam, the bigger value of y is to be used. Now, we have also discussed the certain problems related to the strength of section. Let us recall in 1 minute. The strength of section means the moment of resistance offered by the section, and the moment of resistance is given by M is equal to F max into Z. Here M is equal to the moment of resistance offered by the section, that is, it is the maximum bending moment. Also, moment of resistance offered by the section is maximum when the section modulus is maximum. Hence, section modulus represents the strength of section. We have, I think, studied, or we see the overview of these problems up till now in the last lecture. Let us shortly or briefly revise these problems over here at this platform right now, and then we will solve the more numericals. A beam which is of a square section of the side A, and if the permissible bending stress is F, find the moment of resistance when the beam section is placed such that the first one, the two sides are horizontal, and B, that is the one diagonal is vertical. We have to find out the moment of resistance. Also found out the ratio of the moments of the resistance of the section in the two directions. What does it mean? The question is, or the intention is, that a beam is there in which the section is of square section, which is lying like this. This is the first position. The sides are horizontal, two sides are horizontal, and intention is to find out moment of resistance. The second case, where one of the diagonal is vertical, so it's obviously the other diagonal is horizontal, and intention is to find out the moment of resistance. So in the first case, in the previous lecture, we found out the moment of resistance offered in the first sections when the two sides are horizontal. Then we found out M1, that is the moment of resistance, is equal to F into A cube by 6 as Z, the one, that is the section modulus is A cube by 6. Now in the second case, the intention is to find out the moment of resistance, and which is directly related with the section modulus, because the F which is given is the same for both the section. Means my section is made up of the same material. F is remaining same. The intention is to find out in the second case about the value of Z, Z2, and we know the formula I by Y max. For the triangular, we know the value of I, BH cube by 12. If we consider the two triangles, the top one and the bottom, we got it the BH cube by 12. Divide by Y max, and Y max is nothing but the A divided by root 2. Please refer the previous figure. We have already understood this problem. So we found out in the second case the moment of resistance is equal to F into A cube by 6 root 2. And we found out the moment of resistance in the two different positions for a square section by m1 m2, that is ratio m1 by m2 is equal to, we found out 1.414. It means that the moment of resistance for a square section when its two sides are horizontal is higher of 1.414 times than the moment of resistance that is offered when one of the diagonal is vertical. I wish you have understood this problem precisely, clearly. Let us go ahead with the next problem. Prove that the moment of a resistance of a beam of square section with its diagonal in the plane of bending is increased by flattening up and bottom corners as shown in the figure. Also, the moment of resistance is maximum when y is equal to 8a by 9. Find the percentage increase in moment of resistance. Very good questions which has been asked over here. Let us be understood what data which has been given to you and what we have to find out or what we have to prove. First, prove that the moment of resistance of a beam of a square section with its diagonal in the plane of bending is increased by flattening up. Here one square section is there whose one of the diagonal is vertical. Now, what the statement made in this problem is that the moment of resistance of the section is increased by flattening up and bottom surface. Means what I have to do, I have to cut it down this small triangle portion AEF, so this part become flat. I have to cut it down this portion and remove it so that this part become flat, and my new sections which will be available is this one, EF BHGD. The question is about the y, that is the distance from the CG to the EF, that is the y, is equal to 8a by 9, then we can achieve maximum moment of resistance, and that we have to find out. Yes or no, that we have to prove over here. Also, we have to find out the percentage increase in the moment of resistance. So, what the questions, let us be understood the questions on this tabletop over here, please. What the thing which has been given to us, one square section is given us, please, on the tabletop. This section is a square section. Now, it's one of the diagonal is vertical. The thing is tell in this statement, in this particular problem, is about if I would like to become a flattened top portion and the flattened bottom portion, so my new section is available this, the strength will be increased, moment of resistance will be increased by flattening top and bottom. So I have to make it this portion as a flat. This is the statement that we have to prove. Also, the question which has been tells us this distance y is equal to a to a by 9, we achieve maximum moment of resistance. This we have to prove. So now let us come to this particular PPT. Now, figure shows a square section with the diagonal AC is vertical. Let AEF and CGH be cut off. Refer the figure previously. Let this AEF and CGH will be cut off. I have to remove this section, and the section will be visualized as shown over here. Let I1 is the moment of inertia of the square ABCD about the diagonal BD. About the diagonal BD. If you refer please over here, this is the diagonal AC, this is the diagonal BD. I1 is the moment of inertia related to this diagonal. Z1 is the section modulus of the square section ABCD about BD. M1 is the moment of resistance of the square ABCD, while I2, that is the moment of inertia of the new section with cutoff portion, that is moment of inertia of DEF BHG about the diagonal BD. Please refer this figure. That is M2 about this diagonal BD, but my new section is D, E, F, B, H, G and D for this section. Similarly, Z2 and M2 respectively of the section modulus and moment of resistance. Now, if we referring to the figure A, diagonal AC is equal to 2A, which is given in the data. The data has been stated that we know the one of the diagonal is 2A. Obviously, diagonal BD is 2A. Both the diagonal size is same as far as the square section is concerned. Now,